All right, welcome back, everyone. Today we have Boris Ivanovic coming to give us a talk from NVIDIA. Boris is a senior research scientist and manager at NVIDIA's Autonomous Vehicle Research Group. His research interests include novel end-to-end autonomous driving architectures, sensor and traffic simulation, AI safety, and in general, the thoughtful integration of foundation models into the autonomous driving stack. Prior to joining NVIDIA, he received his PhD in aeronautics and astronautics under the supervision of Marco Pavone, and he has a master's in computer science, both from Stanford University. And today we're going to hear about behavior prediction, a nucleus of modern AV research. You can take it away, Boris.
Thank you very much, Andrea, and thank you everyone for attending. So yeah, the title I think sounds very broad, but that's also because I have kind of a special place in my heart for behavior prediction research. It was one of the major focuses of my PhD, and I've been doing it now for some years. So take a little bit of what I say with a grain of salt, but I think this is indeed an accurate description of behavior prediction. So as we get into, the content, I know you guys have been, from what I understand, covering behavior prediction as a topic in the course for the past few weeks. And, as a quick recap, basically what I think of as behavior prediction is predicting the plausible futures of agents, at least in the autonomous driving case, surrounding the ego vehicle or surrounding an ego agent or whatever robot of interest is.
Oh, 1 second. It says people on Zoom can't see the slides.
Can everyone see it in the room?
We can see it in the audience.
Anna, can you see them?
I can't see them. I thought they weren't shared yet.
Let me just try resharing them.
Yeah, go for it.
See them now as well.
You can?
Yes.
Okay.
Okay, perfect. Thank you very much. So yeah, basically this is what, to me, behavior prediction looks like, and at least in the autonomous driving domain, kind of what it could look like, right? If you're trying to predict maybe multiple futures for different agents in the scene, and we'll talk about some of these things. So as I also saw in your the notes that from, I don't know if it was last lecture or a few ones ago, you guys have kind of seen what the landscape of behavior prediction looks like from a paper from 2020. This is a slightly different figure, a slightly more simple one, but basically it's a similar hierarchy of different methods for trajectory forecasting. So very broadly, they can be broken down into ontological methods or phenomenological methods. Ontological methods are basically methods that assume some kind of structure about agents or the environment and how they interact, and then basically roll forward a model with those assumptions. And so a good example here is maybe state space models, which assume, let's say, social forces repelling different agents, or IRL based methods, which assume a certain form of a cost function. Down on the right, we have phenomenological methods, or these are also sometimes known as pattern-based or data-driven methods. And then within these, we typically have deterministic regressors, which just predict, let's say, one trajectory for each agent, or generative approaches, which either predict multiple samples, a probability distribution, etc. And this figure I lifted from a blog post that I wrote in 2020, but this is kind of what the landscape looked like in 2020. And what I can tell you is that since 2020, at least one of these branches has grown significantly. And we're going to talk about, I'll start by diving into some of the reasons for this and what kind of the new landscape looks like. And then we'll talk about, some broader expansions beyond there. So today, what I want to talk about is, first, I'll give kind of let's say, an update from 2020. What do modern behavior prediction approaches look like? And I'll talk about some of the, let's say, 3 core choices that models have made since 2020. Then I'll talk about some of our latest work in new capabilities for behavior prediction models. And then I'll discuss how that has kind of expanded into end-to-end driving and applications even beyond just the AV stack itself. And this is where kind of the title, A Nucleus of Modern AV Research, comes into play, because I think although these are, some might say, very different research fields than just behavior prediction is really at the core of each of them, and we'll see how that looks as we go. So let's start by taking a look at some modern behavior prediction approaches. And the way that I figured would be a good way of doing this is to do it how maybe someone from outside the field might say, okay, I want to know what are the best models right now, what are the best performing ones, where, let's just like find that out. And so, okay, if you take a look at the Waymo open motion data set, which has itself a prediction challenge every year, if you take a look at the top leaderboard, this is, what it looks like. And okay, maybe these titles aren't very descriptive, but I can tell you all of those ones that have the TR or, like MGTR, MTR, MGTR, and then all the other ones inside, they typically use a transformer architecture, or at least that's where they steal the TR in the title from. And if we look, okay, so this is the prediction challenge. If we look at another challenge in the same data set, we also have a lot more of these now, titles where you see it's kind of like interaction former or tra-jeglish or something like that, which, kind of hints that they're using transformers under the hood. And even if we just take a look at some smattering of recent papers from, let's say, 2021 or 2, all the way up to even this year, like coming up at this iClear in 2024. This is kind of what the architecture diagrams look like. And here I just picked 3 papers from these papers up in the title. And okay, maybe it's not obvious on the top left. Well, at least the title is way former, so it's you can guess that there's a transformer involved. On the right, if you have really good eyes, you can see in the small text it says full attention encoder and causal attention decoder. And then on the bottom, it's a bit more obvious. You can see that they're explicitly calling out that they use a transformer decoder layer. So the first really key, I would say, update from 2020 is, just as transformers have supplanted RNNs for general sequence modeling tasks, especially so in NLP, natural language processing, they have done the exact same in behavior prediction. And the reasons are the exact same, right? In language modeling tasks, researchers saw, okay, transformers can scale much more. They can be run all in parallel, and they generally are able to use, they're able to better use the parameters that they have at hand. And so they, get to scale, as you increase data, they do indeed keep performing better and better. Those same reasons also apply to behavior prediction and general temporal sequence modeling. And so, they've also, whereas maybe in 2020 and in the past, you would see much more LSTMs, RNNs, GRUs, these kinds of model architectures being used for deep learning-based behavior prediction. Nowadays, I would say really it's 99, if not more % transformer-based models. There was a little bit of time where you saw graph neural networks being applied. That was maybe, for one or 2 years. And that's because, you could model the world as a set of nodes, like the agents as nodes and their interactions as edges. But if you think about it, the internals of a transformer, and I don't know how many of you know, let's say, the deep internals of a transformer, but a transformer effectively models a complete graph because its attention is an n-squared attention. So it effectively models a complete graph, which means it basically is a superset of what you can do with a graph neural network. So they've also kind of supplanted those types of methods. So that's, I would say, the first kind of key difference from what the landscape looked like in 2020. The next thing is that there's been a big shift in the choice of input representation. And on the left here, I'm showing a very common architecture that you would have seen in 2019, 2020, 2021, even up to 2022, where you basically rasterize your scene context. And here, rasterization just means you're converting whatever it is into an image. Typically, it's a top-down, also sometimes called a bird's eye view image. And this was true, for example, of sensor data, like, on the left here, you can see it's visualized LiDAR data, as well as map information. So, if you had an HD map from your data set or your company was collecting this, then you would also just rasterize that in the same kind of, let's say, coordinate scale, concatenate all that together, pass it through a fairly large CNN to featurize it. And there you go. That's your scene context encoded. And that was very, very popular up until, I would say, maybe 2022. Then, as the transformer model became much more widely used, so too did vectorized representations. And vectorized representations here is just a fancy word for taking directly the, let's say for maps, the underlying polylines, or taking directly the positions of where agents are for trajectories. And I want to ask here the audience, I mean, besides the obvious, like, maybe, okay, it plays better with the architecture. Can you think, or could you shout out any reasons why vectorized representations might be better than rasterized representations for encoding scene context? Yeah, go for it. I can see you in the green shirt.
For the especially like say a long distance objects, the vectorized it's trivial for the vectorized representation to like sort of represent it. But if you just say like represent something 1,000 meters away, the raster would waste a lot of empty spaces, and it's more compute efficient.
Yep, that's definitely one thing, and you can even see this on the left image, right? Where, I don't know, 40% of pixels are just black. I mean, it's probably actually much more percent, but basically you end up encoding a lot of not relevant information to your task at hand. So that's definitely one. Any other reasons?
I'm here from Zoom. It seems like input dimensionality is one of the reasons, because you have such a sparse representation in your kind of the rasterized representation. It makes sense to just actually make it sparse and make it vectorized.
Yep, this is exactly, and I think, and you can tell, right? These two reasons are very interrelated. It's really about either you could call it sparsity of information, or maybe more the highlighting of only really what's relevant information. And so, for transformers, which can directly attend over, let's say, these kinds of sparse objects, it's much, much, much more efficient to just pass in, I don't know, let's say the 50 polylines that represent the map around you, rather than the 200 by 200 pixel, top-down rasterization, which with however many channels that might be, to encode the same information. So yeah, exactly. So this kind of a representation is now very common, and you can see this, right, in papers if you look at kind of their encoder architectures, and which I've pasted here as well.
Boris, have people also studied like robustness of these different input representations? Like, are vectorized forms more robust? Like the classic, you have the panda image, you add Gaussian noise, suddenly your model can't do anything. Is that true here as well?
Yeah, this is a good question. So as you can appreciate, it all will depend on basically what kind of noise we're talking about here. If we're just talking variance, like a zero mean Gaussian, I think in both scenarios, right, for a rasterized or polyline, like your model will be able to simply learn to either filter out, or it will learn, right, how to handle this. If you have bias, it's hopeless in either way, right? Because I mean, there's nothing your model can do other than learn to maybe ignore let's say your map input in that case. Yeah, Abhijat?
Yeah, I also wanted to chime in on that point that one thing that we've seen, I've been working on sort of adversarial attacks on some of these policy models, and black box attacks are more efficient on these smaller input representations. which is something to be wary of, I guess. Like, but yeah, that's just natural. So
Yep, yeah, exactly. Less information, easier to, then the less of a change you have to enact in that representation to affect the output. That totally makes sense. Now, the other major change, kind of the third in this major change, is the factorization of the problem. When I say problem here, I'm referring to modeling the future of agents. I would say prior to 2020, maybe even 2021, it was very, very common to take a marginal approach. Marginal here means predicting each agent's future independently. And what that looks like is, okay, so if we have this scene on the left, it means that you would predict, let's say, a set of trajectories for each agent, and then maybe pick the most likely one and say, okay, this is what's going to happen in the future. The problem with that, as you can very, probably quickly appreciate, is that each agent's most likely future, it might be completely sensible in isolation, but now when you combine it with the fact that there's other agents in the scene, you can get very unlikely outcomes. And that's because, of course, there's actually in reality, this is a joint modeling problem because there's multiple agents that are interacting that, will have to respond to each other. And so the other switch is basically one from switching from a marginal problem factorization to a joint problem factorization, which is where you're trying to predict multiple agents' futures simultaneously and basically tease out these two different interaction modes rather than just saying, oh no, they're just going to go forward because that's their most likely move. It's like, no, one is probably going to yield to the other. And of course, there's been a good amount of papers on this topic. So that's kind of, fast forwarding the landscape to today. That's at a very broad level, let's say what the differences are to maybe what you've seen in lecture, but what you will see if you dive into some recent papers. So with that in mind, I want to now dive into some of the, basically new things and kind of branch out what can behavior prediction, do, novelly now and how it kind of has expanded, beyond just predicting, the futures of agents for, let's say on vehicle driving. So the first topic that I want to talk about is generalization. And in particular, this, all of this progress in the field is very encouraging, but typically when we're training these models, we're only training on data sets that are, I don't know, from San Francisco or from, where else in the, specific cities in the world. The problem is the world is very large, right? And you want to try and actually generalize these models from where you've trained them to other parts of the world. And the thing is, there's very different behaviors that you can, run into, right? There might be different customs of how drivers drive together. There might be very different laws which yield very different behaviors on, like, if you have a German traffic jam, you have to create this lane in the middle. Or there might be vehicles you've never seen before that you kind of have to deal with. So in the first work that I'm going to talk about, one of the questions that we asked in the group was, can recent advances in meta learning help us? Basically, can we generalize by simply enabling the model to adapt to its new environment? And meta learning here, for those of you who haven't seen this term before, it's basically a recent paradigm or kind of type of learning approach that allows models to very rapidly adapt online after having observed a little bit of data. And so the question here is, can we infuse this concept into trajectory forecasting methods to enable them to adapt online? And what we did last year in this topic was we basically took a Bayesian meta-learning approach. And if you ignore the jargon, really what we did was in most prediction models, you have something that looks like an encoder, some internal latent representation, and then some decoder. And what we did is we simply replaced the last layer of the decoder with a Bayesian linear regression layer, which is, it's basically just a matrix. It's just a linear layer, but the weight itself can be updated online. And so during training, what you're doing is you're trying to optimize your network weights to learn the prior distribution of that final layer K. And then at test time, you can update the posterior distribution of K actually via very simple via Kalman filtering. And you know, you don't actually have to change the rest of the model's weights, which means you get very efficient updates. And just to kind of instantiate what that looks like. So here, if I take the, you know, a behavior prediction model from a few years ago, you know, there's a lot of stuff going on, lots of encoders and all this, but at the decoder, if I just take a look at this final layer, this KZ, which is kind of the last linear layer before some dynamics integration happens to position, if I only update this K with new data, then this is already, like new data online, this is already enough to basically make the model adaptive to what it's seen. And I'll talk about, you know, what this looks like here. So, you know, in addition to just this kind of quick architectural change, one of the core contributions that we had was to change the sampling strategy by which you get an actual output from the model. And, you know, I know that there's a lot of math going on here, but really the heart of it is we're doing something very similar to Kalman filtering, where we are sampling a value of this K last layer matrix. We are then computing our prediction of the next state. And then effectively, we are checking, you know, after one step, we are checking, okay, how good was this prediction compared to what we actually observed, you know, after just waiting one step. And then, I mean, that's, you know, welcome to Kalman filtering, right? You're basically checking how your model is performing as you're actually, you know, moving along, and at least for Kalman filtering, it's tracking something. But here, right, you're effectively just checking how well your weight matrix here is performing. And the good thing is, on the loss side, we don't have to change anything. This is all purely a way that you sample from the model. And so at loss time, we're just maximizing log likelihood, which is what a lot of these probabilistic prediction models are doing anyways. So what this looks like when you actually run it, so online on the left, you can see what I did was I trained the model on one data set, in particular this new scenes data set, which has a data frequency of 2 Hertz. Then I transferred it to another data set, which is the Lyft data set, which first of all has different cities, but also has a different data frequency. And what you can see how this manifests is at the very first frame, do you see how those kind of blue hazy clouds are really like way overshooting the kind of even the image, you know, the patch of the map that I'm showing? That's because, you know, for 2 Hertz, it's expecting much more motion compared to what you see in 10 Hertz per step. And so what you can see is after just a few steps, this is basically 1.5 seconds of real-time driving data, the model is very rapidly able to adapt and be like, okay, I'm really wrong at the beginning, but, you know, over time, I'm actually able to bring these predictions much closer to the actual future motion of the vehicle. And I mean, this is also borne out in the quantitative plots on the right, where you can kind of see this blue line, or the blue line is kind of the error versus online observed data. And you can see after just a handful of time steps, this error is all kind of trending down towards the Oracle, which is a model that was just trained on the data set that, you know, I'm transferring to. And you can also do this offline. You don't just have to do this online. Maybe you have some data that you collected in hand from you know, some time ago, and you want to adapt offline. You know, the same idea applies, right? You can all do this either offline or online. It's just a bit nicer offline because you can do it in a batch form, so it's a bit more efficient. Now, are there any questions about this adaptation idea before I move on to end-to-end driving? Yep.
I would imagine this method is sort of very rapidly like optimized due to the current situation. But say if anything like kind of say a pedestrian jumps out of the side, that type of stuff, would this like fail to quickly adapt those scenarios in time?
Yeah, this is a good question. So basically what, yeah, you're kind of saying like, this is good for, let's call them like lower frequency changes versus high frequency, like transient instantaneous changes, right? And I think that's true, because even for like a Kalman filter, right? If you get one outlying point, like along when you like when you're tracking a trajectory, if you get one outlying point, your Kalman filter, it's going to do a good, like it's going to actually just try and keep that mean estimate close to the the bulk of the other reasonable, like it's reasonable prediction that you've seen, especially if the next point or the point after that you get are more reasonable, right? So here, I think the same idea applies. If you have some instantaneous, like transient change, I don't know, some agent on the road or something, then the hope is that your model, because it's a prediction model in and of itself, it's going to, predict to avoid, maybe even instantaneously, just to, like, it's going to predict one trajectory to avoid. But then if that, let's say that agent, is out of the road, or let's say the situation is resolved in like the next 1 or 2 time steps, then everything's just going to snap back to normal. So there, I think basically that kind of adaptive last layer, it's probably not going to be doing much, to be honest. Because if it's just a transient update like this, then it's kind of going to be averaged out. Yep.
This isn't like a super deep question or anything, but with these like really powerful, I guess, like transformer-based architectures, like I noticed that lift is like recorded at 10 hertz. Is inference actually being like done at 10 hertz?
Yeah, this is a good question. So actually, inference, you typically want it to be done as fast as your general like autonomous driving stack is running at. And so there's a few things. There's the, I'm going to call it the, we can almost say basically the refresh rate, like how fast you can actually run your model. And then there's the, like, there's your let's say your output trajectory frequency, right? Like maybe I can run, let's say I can run this model at 10 hertz, but I can produce 60 hertz worth of points, right? It's going to be dependent, like what does your downstream, let's say planner or controller, how fast do they run? How frequently do they need points? So I would say typically your output, let's say frequency, you want to match that to what your planner and controller can do. And then for your input, for the actual refresh rate of your entire algorithm, you typically want that to match your perception refresh rate. And the reason for this is because you want to update your predictions when you get new data. And that's, typically at the tick rate of your perception. So it's possible, very possible, to have 2 of these tick rates. And yeah, I mean, the reason for new scenes versus lift is the difference is, at least in the data set side, new scenes is hand labeled. And so they, they're not going to label all 10 hertz, frames, because that would be pretty ridiculous. But lift is auto labeled. And so they can easily get 10 hertz worth of agent object detections and stuff like that.
Here's a question in the back.
So after adaptation to new environments, did you test it back on the train setting? Like after this adaptation and fine tuning, how does it perform in the initial setting? And is the idea here to do some sort of continual learning such that it can perform well in all the environments you test, or just have a collection of a bunch of fine tuned models?
Yeah, this is a good question. So I expected it would perform worse on the original data set, right? Because you are very particularly focusing on, the let's call it the task at hand versus your original one. So this is actually on purpose. And the point of this work is kind of when you want to deploy this in a new environment for which you have either very little data or maybe no data, you are going to have to, if you have nothing else at hand, you're basically just going to have to learn it as you go, or learn it online or adapt online. Now, in terms of bringing that back home, to some mothership or to some home server, there are ways that you can combine, if you guys have heard of federated learning, this is the concept, right? Where you can try and learn, let's say 7 different models in 7 different data sets, but then try and bring what they've learned back, and synchronize them. You can do this. We didn't explore this in this work, but you can definitely do this, if you want to try and scale out, let's say the geography with which you can cover at a base versus, like in your base model versus just adapting it every time. So the way I envision this is, you would adapt this for, I don't know, 10 seconds or maybe a minute or something like that, and then kind of keep it frozen and say, okay, probably we're kind of happy here. We don't want to keep updating the learning, or at least you're not going to get much benefit from updating the learning. That's kind of the mental model I had in mind. Okay. With this, I'm going to move on to the next topic, which is end-to-end driving. And in end-to-end driving, I think there's kind of the first thing that maybe immediately comes to mind is, okay, our architectures for end-to-end driving, where here on the left, I'm showing, I would say, like a standard or a traditional autonomy stack where you have kind of a cascade of different modules feeding their outputs into each other. And then on the other hand, for end-to-end driving, you could just say, okay, I'm just going to pass my sensors in as input, get my motion planning as output, and hey presto, that's my end-to-end, learning-based autonomy stack. Now, that's kind of one form of end-to-end driving, but actually another form of end-to-end driving, without even going so far as to change your architecture, is to do something called metric coupling. And we're going to talk about this first a little bit, but the core idea of this approach is, okay, if I'm able to evaluate, let's say, my perception module in isolation, my prediction module in isolation, that's great. Let's say they perform very well. Unfortunately, that still doesn't tell me how well the system is going to perform if I put perception feeding into prediction, which then feeds into motion planning. And so even if you don't want to touch your architecture, you can still have end-to-end driving behavior by making these modules aware of their downstream task. And we're going to talk about one potential way to do this. And then we'll talk about architectures for end-to-end driving. So the first thing that I want to talk about, so on the left here, I'm showing kind of a smattering of very common behavior prediction evaluation metrics. You may have seen these in some of the papers you've read, like the average displacement error, the final displacement error, the negative log likelihood, the minimum of whatever, right? Like this is kind of what they look like, and at least graphically, this is how they're depicted. However, while this is maybe reasonable from like a metric computation perspective, from a semantic perspective, it's a little bit task agnostic. And the reason I say this is because take this example where a car is turning to the right. I've drawn a little circle, which is kind of, let's say, equally wrong in L2 space. But the problem is there's different amounts of wrongness, right? If you have a misprediction that's close to your ego vehicle, that's much scarier than if you have a misprediction that's far from the ego vehicle, right? And so there's this kind of task awareness that we actually do want to capture in our metrics, which, let's say, current metrics don't capture. And that means that your predictor might be very, unaware of how its predictions are affecting downstream motion planning. And so in this work from a few years ago, we kind of set out to identify a better way to bring this task awareness into evaluation. And what we kind of started by outlining a set of core desiderata, like, the first one is obviously we want to capture asymmetries in downstream tasks. But we also while we want this metric to be task aware, we don't want it to be method aware. Like, I don't want to care that the motion planner is using I don't know, a certain formulation of MPC, or it's a certain sampling based motion planner. That wouldn't be good, right? Because then it's not widely applicable. We of course want it to be computationally feasible and ideally human interpretable. And this here is a very fuzzy concept, but hopefully you'll give me some rope here. So the core idea that we explored was, okay, if we want to avoid being method aware, but we still want task awareness, we said, okay, we figured the downstream task of motion planning, typically you have a motion planner, but what the motion planner is doing is it's minimizing a cost function. And that cost function is basically capturing what you care about in terms of how your subsequent motion is generated. So, okay, we can keep this idea in mind, and we can actually, basically say, okay, can we make our metric planner cost function aware? is kind of the question. Okay, maybe there's a way of doing this. So the way that we did this was, the way that we thought about this was, okay, let's break this into 2 steps. Let's first identify a planning cost. But again, I don't want to pick a particular one. I would rather try and stay as broad as possible. So I'm going to see if we can learn a proxy planning cost from data. I'll talk about how. And then could we take the gradient of this learned planning cost to get a sense of sensitivity, right? How sensitive is planning to my prediction outputs? And then this gives us at least a notion of, okay, how much my predictions will affect planning, or at least my prediction errors will affect planning. And so the core idea is to take some human motion data and a set of cost function terms, run something called inverse optimal control, which is exactly the same as inverse reinforcement learning, by the way, to learn planning cost function weights from data. And when I say learn here, I'm saying that these cost function weights kind of best reproduce the observed trajectories in the data set. And then once I have this magic, these magic numbers that I can then, linearly combine my cost function terms with, I can take the gradient of this formula and see how it's I can see what the gradient is with respect to my predictions. And that's kind of the very overarching idea, is that I'm going to learn a proxy planning cost that hopefully represents human motion well. I'm then going to take its gradient to see how my predictions change, or how my predictions affect that. And this basically gives you this sense of something called planning sensitivity, right? How sensitive the ego agent's planning is to changes in my predictions. And the cool thing is you can actually see, after doing this, you can actually see that it kind of, at least I would say, kind of works, where I can identify. So the colors here, so red is a detection. Actually, let's look at the prediction cases here. So blue is the ground truth, and then you can see some predictions here. And then the more red, basically the more sensitive that a planner is to that prediction, and to that agent, I should say, to that agent's future. So here in this scenario where like a vehicle, like the ego vehicle is coming to a crosswalk, you're able to see that like the pedestrian that's going to enter the road is basically this ego agent is like most sensitive to that vehicle. Or here with pedestrians, right? These pedestrians are most affecting the ego vehicle's motion. Or same thing right here, if you have some pedestrian walking onto the street, that's maximally affecting of the ego vehicle's motion. Okay, cool. Let's say that we have this planning sensitivity in hand. Okay, I talked about metrics, right? How do I use this planning sensitivity for metrics? What you can do is, yes.
I have a quick question.
Yes.
So we had a lecture from Lasse last week on game theory, and when describing, how one does planning in game theory, there was a similar question of, assume I fix my trajectory. I'm asking myself, how is my cost affected as a function of changes in the other agent's behavior when I'm searching for like an equilibrium, right?
Yep.
Have you guys thought about like is there a either explicit or implicit connection to game theory here? Like this is kind of like like a specific type of game in this meta word space.
Yeah, so I would definitely say the connection is implicit here. Look, I know very little game theory, I have to be honest here. So, for me, I was borrowing much more. And Andrea, I mean, I was asking you these questions back when you were working on this. So I was borrowing much more from the IRL and the IOC literature and the concepts there. So very much in the, if you remember the kind of tree of methods, very much in the ontological space of behavior prediction here, I'm explicitly assuming, let's say some terms that agents may care about, and then doing something with those terms. So to me, the deep connection is with IOC or IRL, but game theory fits very nicely in there because I think game theory, you have these same formulations, right? Of how agents are moving around, or their motivations, or whatever their rewards. So definitely an implicit connection, but I don't have many, let's say, deeper thoughts along that space.
Thank you.
So how can you bring this planning sensitivity into metrics? You could do it one of 2 ways, internally or externally, or I mean, I guess both. But internally, what you can do is you can change internal metric thresholds. So one example is if any of you have done detection, object detection before, typically you have something called an intersection over union limit to what you count as a true positive detection versus a missed detection. And that threshold you can scale based on how important, like based on the planning sensitivity of that agent, because that's effectively how important it is to get it right. And what you can see on the left is the normal, precision recall curve that you get with, normally chosen IOU. But on the right is my modified IOU, so that you have to be more accurate for more important agents. And you can see how it kind of actually shifts the metric. Then on the bottom, you can also do external injections of this knowledge, where you can striate existing metric values based on, different planning sensitivities. So for example, if I'm measuring the average displacement error of agents in a scene of my predictor, I can say, okay, don't just tell me the average number for the entire scene. Tell me on the agents for which it's highly planning sensitive, how am I doing? And then, for the other ones. And the cool thing here is, so here I evaluated, again, that same model from before, Trajectron++. Again, this was a few years ago. And I can see, thankfully for me, that the model actually performs better, i.e. has a lower error on agents where it matters. So that's, that's good. That's good to see, right? It would be worse if the error was higher. And then it's okay to have more error on agents where they're less, let's say, impactful to the ego vehicle's planning. So cool. I'm happy with that. Now,
Here's a question.
yes.
Or maybe just after you finish the next, because I was going to ask the next slide.
Okay, yeah, well, perfect segue. So the other, of course, big, way of having end-to-end driving is by literally changing your architecture to be more end-to-end. And so end-to-end here. So this is, again, the traditional stack that you may have seen in not just AV, right? You see this in robotics, you see this all over the place. And this is what I would call a modular AV architecture. You have cascades of modules and they each do their tasks. There are specific things and then they feed into each other. Great. On the other hand, end-to-end AV architectures are typically those that, will try and, let's say, directly regress your motion plan from input data or from input sensors or whatever. Now, I think in the past, this used to be viewed much more as like a big dichotomy. Like you're either modular or you're either end-to-end. And I think in kind of the past 2 years, it's actually, more insightful and more common to view these as parts of a spectrum, as ends of a spectrum. And there's kind of a lot of choices in between of how much end-to-endness you bring in. And something in the middle, when I say end-to-endness, I'm really referring to how differentiable, right? How much can you propagate gradients? How much can you propagate information from your downstream task at hand up to your input sensors? And so a stack in the middle might look like, okay, I'm going to do my modular architecture, but I'm going to ensure that each of those modules is differentiable, so that at least I have my, a modular architecture which I can reuse in different places. I can interpret the outputs of the intermediate outputs, but I can also propagate the downstream task upwards, which is nice. However, all I'm showing you here are nice, pretty pictures on a screen, right? How to actually choose what, architecture you're building is a huge question, right? There is a big question in choice of modules. So, okay, are you going to, if you are doing, let's say you want to have, your perception, what's the output of your perception? You can do it as like a 3D semantic occupancy, right? Which is very dense. This is almost like that rasterized choice of representation. Or you could do something more sparse, like, okay, I'm actually only going to produce, each individual agent's future motion and just their detections for where they are, which is a bit more of a sparse choice. And the thing is, I think I said earlier, like, okay, it's kind of, everyone has kind of moved towards, let's say, vectorized. But even nowadays, and these are last year, I'm showing 2 paper references, papers that are presenting state-of-the-art results that are recent, modern, and yet they both they have different choices for these representations. So I presented a binary picture before, but I would say the jury is kind of 80% out, where it's definitely in isolation, one representation is typically better than the other. When you have a whole connected stack, the picture becomes a bit muddier, and you have to now really do evaluation on which one is best for you. But even if you choose these modules, I want to do semantic occupancy prediction, or no, I just want to do occupancy flow. You still have to choose, right? You still have a big choice in output representations. And just like I mentioned before, do you produce a rasterized output? Do you produce a vectorized output? And if you do produce these, they have downstream effects, right? Because planning, if it needs to consume these things, or prediction, they need to consume these things. So do you just take in, let's say, these rasterized, maybe interpretable, outputs, or do you take in something more latent, like literal, latent vector outputs from models? In a transformer case, it would be like taking their queries rather than taking, interpreted polyline outputs. Still an open choice here. And all of this is complicated by the fact that you then have to actually figure out how to place these. And it's not very evident, right? Because, okay, should mapping feed into prediction? Should mapping feed directly into planning? Or should mapping only feed into prediction, which then feeds into planning? Or should it feed into occupancy prediction, which then feeds into planning? Et cetera, et cetera, et cetera. There's a lot of choices here. And, it's very difficult to simply explore this because, it's quite expensive and it takes time to train these things. So, long-winded, but I just want to explain that there's actually, once you get into the realm of, okay, I want to bring this thing into the stack and I want to change the architecture, there's a lot of things to change. So to help systematically go through this, and this is hot off the press, I yesterday got the email that this paper was accepted to CVPR this year. So I'm telling you, this is recent research here, is what we did was systematically explore this design space. And we looked at 3 axes. The first is necessity. So which of these modules are actually essential for driving, and is there any redundancy? And don't worry, I'll bring this back to behavior prediction. The second is placement. How should I place these modules? And the third is representation, right? Should the outputs be latent? Should they be interpreted? Should they be a hybrid of them or whatever? And I'm showing here 3 papers, again, from last year, which all report state-of-the-art performance, very strong performance. And yet they all look very, very different with very different choices. So in order to do this, we built a flexible computational driving graph, which we're going to, of course, open source for everyone to use. But we built this computational driving graph to help explore this design space. And what we did was, so, okay, we started by saying, okay, let's re-implement, methods from the literature and then start there. And then, we'll work our way over. And so, okay, we were able to see, if you look at the full validation set of, in particular, this was the Nucleus data set that was being evaluated in an open loop fashion. Okay, we kind of see maybe let's say a consistent story, although it's probably not ideal that the off-road rate is kind of slowly climbing up, but okay, maybe we'll address that later. Oops. What's interesting is if you just look at targeted evaluation, so you don't look at any scenarios where you just drive straight, because that's very easy to predict, right? The story is very different. And I think this is kind of interesting. This is not even to call out any papers or anything like that. I more want to illustrate for everyone here that even in state-of-the-art research, the question of how to evaluate and what you should pay attention to when evaluating an end-to-end driving stack, it's pretty open, right? There are 3 papers, you'll get 3 different arguments for why, no, my way is the right way of this is the right data set to look at. This is the right subset. This is the right metric. It's open. And so, we made some standardizing choices to at least evaluate across these different stacks. And if you're curious, I can tell you. But what we did was we started with the most complicated of these models, UniAD. And we said, okay, let's play around with the architecture and see what happens here. So what was very interesting was when we actually removed this flow of information between mapping and prediction and occupancy prediction and planning, performance improved. So it was like, okay, all we did was remove actually capacity of the model, and yet it performs better. So that was kind of interesting. And we saw kind of the reason. We have some hypotheses for the reason why, but suffice to say, if you try and change the model from that point forward, you actually get nothing. You don't really get that much performance differences, even if you play with the representations, if you play with the, which edges are there or not, you actually don't get anything. And so then the question we have is, okay, maybe there's this like, maybe we've reached the quote unquote, the minimum, right? Like the necessary minimum in order to do end-to-end driving. And to really connect it back to behavior prediction, again, this is behavior prediction is the nucleus here, right? Is interestingly enough, occupancy prediction and motion prediction are, if you use them in a sequential fashion, like, where your perception output features feed into motion prediction and then feed into planning, you can ignore the other one. And this works vice versa. If you have one of these predictions in your chain, the other one is redundant. However, if you want to do something a little bit crafty and you actually want to just create a more parallel architecture, parallel here just means I have multiple, let's call them auxiliary tasks versus the main task of motion planning, for end-to-end driving, then both of them are crucial. You cannot touch them. Otherwise, your performance drops significantly. And so here, behavior prediction is actually quite vital in order to learning the correct information you need in your output representation from perception in order to do motion planning. And what we did in this paper was we said, okay, let's take these learnings into account and simply design a parallel architecture, which basically maximally informs its latent space. But then online, if I only care about motion planning, I can maybe even turn off the other heads and maybe save some computation time. And, if we follow our same story, and I can, show the plot on non-straight driving, but you can see, even with this, we now significantly outperform some of these other methods, right? Again, with a simpler architecture, which is great, right? We're very happy about this. And the best part, like I said, so okay, this is the, typical, I'll show you kind of what it looks like when this runs. But the best part about this is not so much, okay, you'll see this in every paper, but when you compare this to, the original approach that we started from and that we pared down, for the exact same performance, or actually better performance, right? Look at the difference in speed. I don't know how this shows over the internet to you guys, but for me, that bottom video is like blistering fast compared to the top one.
Yeah, it's
And the
fast.
whole point is, again, because you're saving all this computation. You have it informed your latent space, but you wasted that time during training, not online. And that's, the important part here. So are there any questions before I move on to the final portion here? If not, that's fine, because we'll have, time at the end.
Boris, I have one quick question.
Yes.
The graphs that you showed, were those still on new scenes, or what data set?
Yes. Yes, they were. And they were all open loop. So that's big caveat here, is this is all open loop. And we're actually working on getting closed loop graphs as well into the paper, so that we kind of complete the story, so that it's both open and closed loop.
And you also said that you have plots that were specifically for the non-straight driving.
Yes.
Do the trends hold basically?
Yeah,
Non-straight driving. Got it.
Yeah, like our method is still way better than prior approaches. And we have this in the paper as well.
Thank you.
All right. So the final thing that I want to talk about is, okay, so it might be, kind of immediate in your mind, like, okay, behavior prediction is obviously, maybe I've convinced you, right? Behavior prediction is indeed the nucleus of everything on the stack. And that's maybe sensible, right? Because it's a part of the stack. You could say this of perception. You could say this of motion planning. But I think one of the other big hallmarks of where you can use behavior prediction is outside of the stack. And I'm going to talk about one particular application in traffic simulation. So traffic simulation, as you can imagine, it is basically the problem of simulating the world and simulating other agents so that you can potentially train, but most, certainly evaluate your either autonomous driving stack or your predictor or whatever, without having to actually get a car. And I would say, in the past maybe few decades, we've made big strides in having high fidelity physics simulation or high fidelity rendering of, environments. And NVIDIA itself also has like a product that generates photorealistic, with ray tracing and everything, simulations. However, a missing component of this is having intelligent agents that actually generate realistic, reactive, human-like driving behavior. Right now, we're still very much using state-space models or other very simple rudimentary models that don't have kind of the nuance that real human driving does. So, okay, I just talked for like, almost an hour on behavior prediction, right? So we could do something about this, right? Because behavior prediction is typically modeling human motion. So let's take our best behavior predictors and make them traffic simulators. Let's see what this looks like. So on the left in this video, I'm showing just normal data, right? On the right, I'm taking my excellent, best state-of-the-art predictor, at least at that time. This is 2022. And I'm rolling it out. Oh my God, it looks garbage, right? This is terrible. So it's like, what is there really such a massive gap here? And the problem, actually, maybe I should ask, what do you guys think the problem is here? Why did this super great behavior prediction, my favorite thing on earth, why does it perform so poorly when I put it in a simulator?
Behavior prediction and planning are not the same.
Correct.
And
How do they
there
differ?
is, so, I mean, there's no, it's like a distribution shift, right? Like you have, there's no temporality to your behavior prediction.
That is exactly,
Yeah.
Keep going.
Yeah, you're just not making decisions it's not sequential decision making. It's just like you're taking snapshots, getting a future prediction, and then the next time you're doing that all from scratch.
Yes, and this is really the key term to keep in mind, distribution shift. This kills all learning-based models always. This is why we had to do this adaptation research. This is why, generalization is such an open problem, even in general deep learning. I'm going to break this down a little bit more close to ground. So distribution shift is really, in this case, a problem of compounding errors. My behavior prediction might be fantastic, but it's not perfect with zero error, which means if I generate some trajectory, maybe the first time step maybe has 1 centimeter of error, right? Okay, I'm going to now teleport the vehicle to that new position and feed this back in and run the model again. Maybe now the next position has 2 centimeters of error, or 3 or 4. And hey presto, then suddenly you get 5 meters of error and you're off lane and completely wrong, right? But it's this compounding error problem, which really affects when you take these models trained in open loop and deploy them closed loop. Big thing to keep in mind if you ever do this in your own research, or you need to think about this problem. So in order to, kind of address this problem, we figured, okay, we actually have to think about this problem specifically to simulation. And the few desiderata that we had in mind for what is actually a reasonable, useful traffic model is it needs to be high fidelity, and it needs to be realistic. We'll talk about what that means. It needs to be diverse, because I don't just want to replay something I saw in data. I want to generate new scenarios, right? And of course, it has to be controllable. I don't want to just generate any scenarios. I want to generate specific scenarios. And then, of course, we also have to contend, like I just showed you before, with stability and with potentially long horizon simulations, right? I don't just want to generate 3 seconds. I want to maybe generate a minute of simulations. So I have to be stable over a long time. And in the first kind of our foray into this space, we decoupled the problem, decoupled it into a high-level prediction problem and a low-level prediction problem. High-level here just means I want to predict where the agent wants to go. I'm going to predict its goal, and you can see that on the right here. It's a spatial heat map of probability of where the agent wants to go. And then I'm going to have a lower-level policy, which is going from A to B. That's it. So I've seeded all the difficult, question of probability and multimodality and everything to the high-level predictor. And then the low-level predictor says, okay, I want to get to, to the next position. I want to get to the next position. I want to get to the goal. And this decomposition is really nice, because if you do this for each agent, right? So if I do this, if I train it kind of like in a marginal way, but because I'm doing a closed loop, each agent is now able to do decentralized decision-making, right? It's able to keep in mind, okay, there are these agents near me, so I'm going to try and avoid a collision or something like that. So you get these kind of realistic behaviors, even in complicated traffic scenarios. What you also get is that because there's a bit of stochasticity in these predictions, you can get very different realizations of the future, even for the exact same initial conditions. And that's, kind of an example of what I'm showing here. Now, I said that I'm going to talk about evaluating simulation quality. So how do I even measure realism? Well, open question. There's a few things that we do, which is basically to come up with a concert of metrics to evaluate this. And the concert of metrics here, at least that we use in this paper, and I think what you would have seen in a lot of now papers onwards from this point, is you kind of see these, let's say, trajectory level metrics. Like, okay, am I covering, so coverage on the left is, am I covering a good amount of the map? Diversity is, okay, are my, subsequent rollouts, are they different from each other? And then failure rates, right? Am I driving off-road? Do I have collisions? In terms of realism, you can measure things like, if I generate, I don't know, 100 trajectories from my simulator, for my model, and I compare the distribution of their, let's say, velocities, or of their, derivatives of acceleration, jerk, or their acceleration, how does that compare to real-world collected data, right? So that's something that you see on the second row. And then the final, and this is perhaps the most researchy, very much the most open, is can we even learn, can we have a model that learns what, realism is and maybe gives you a score? Again, this is very still in the researchy side, but at least suffice to say, for this model that we worked on a few years ago, it really hit the marks in a lot of these categories. Now, okay, sure, maybe we have a realistic simulator in hand, but what about that aspect of controllability, right? Or maybe we have a realistic and diverse simulator, but I want to control it, right? I want to generate specific things. So, we looked at other architectures. So, you don't just have to use a transformer, right? There's also, you guys might have heard of diffusion models in recent times. I'm not going to get into what they are, but I'm just going to say we've also explored other architectures and they have their trade-offs. But one thing that you can do with the diffusion architecture is the way that they generate trajectories, they do this in an iterative fashion. And you can actually influence that generation process. And something that we did in this work was we took logical formulations. That's what STL stands for, signal temporal logic. We took logical formulations of like desired outcomes and actually influenced the generation process. And so what this allows you to do is to generate, scenarios where certain things happen. So on the top row, nothing, it's just a normal generation. On the bottom row, I said, I want these cars to stop in these exact positions. And, okay, it might be overkill using such a complicated method, but the point is that, the method is able to learn to slow these cars down earlier, to get them exactly where they need to go, and etc. And, okay, this might be, again, like I said, way overkill, right? Like imagine writing a logical formula to then pass it into some diffusion model to then just get some vehicles to stop in a certain, place. Okay, way overkill, but it sets the groundwork for some very interesting capabilities, like what if I want to feed text into, you may have heard of large language models, and get their output to then generate these rules that then affect my simulation. And if I take it, some prompt like this, I can actually generate very specific behaviors, like I want a specific crash. I want this crash to happen, which I've never seen in my data, but I want it in this specific way, right? I want it to crash into the left side of the model or left side of the car. And, you can do this with diffusion. You can also do this with transformer models. And this is these are two works we had in parallel. And in this other work, we actually literally took National Highway Transportation Safety Authority or Administration crash reports, like text crash reports written by police officers or insurance companies, I don't know who, and we were able to recreate them in simulation, just passing the text into this model. We were able to retrieve a map that kind of reasonably fits the scenario, generate trajectories, place agents in the map, and then generate trajectories. And okay, this is already a useful, let's say, tool at hand, but you can also just do freehand, right, generation. Maybe I just want to generate, okay, let me just generate some sparse traffic. Okay, it will maybe look like this. Generate crowded traffic, generate very crowded traffic. And the cool thing is we don't have to hard code what these words mean because large language models have done this for us, right? They've done this like hard work for us. I see a question in the back.
Um, so when you say generate sparse traffic, there's many different traffic patterns that could count as sparse. How do you evaluate this?
Yep, we just took this is a good question. So the heavy lifting here is done by the large language model. It converts this text into a structured intermediate representation that we then will retrieve a map with, put agents on, and predict where they go. So sparsity here is defined by basically what your large language model says. But if you don't like it, you can also sample other.
I'm asking about evaluation. So how do you know that what you've generated is sparse traffic?
Yep.
Because like if you have a ground truth sort of configuration that you say is sparse, and the model outputs that configuration, great, you won. But the model could output a different configuration that's very different from your ground truth configuration, but still be sparse. So do you have, okay, sparsity is defined by the set of predicates about how.
No. So we had a So the training of this model is where the fun comes in, right? Where basically we had a lot of what we call grounding tasks. So when I say training here, the LLM is pre-trained. We're not touching that. But all the surrounding transformer parts and all the representations that are used internally, we have to align them, right, between the LLM and between our, what our transformer needs to know about the world in order to predict. And we did basically a good amount of it is just, good old fashioned, like we'll like human label some, we'll write out we'll take like some scenario from some data set, and they'll typically come with some very, kind of terse examples. So if you look at the new scenes data set, if you look at the Waymo data set, if you look at the new plan data set, every one of their scenes actually has text associated with it. It's very simple, very sparse, but it has text associated with it. And what you can do, and again, I encourage you to read the paper to see all the details, but what you can do is you can take that text, feed it into something called a rephraser model, which is in this work, we use T5 from Google from I don't know how many years ago. And what it does is it literally takes that sentence and we say, okay, generate 10 different variations of this sentence that all contain the exact same semantic meaning, but phrased differently. And what we can do is then we can have some heuristic functions that, match the, let's say, original, these kind of simple text captions that came with a scene to the actual output trajectory. So this is where you kind of, the human engineering, don't get me wrong, it's still there, right? But it's more at the training time. And then the idea is that you would, because you're aligning to this LLM representation, the LLM then can take you to places where it's not necessarily in your, let's say, corpus of training alignment data. That's, I would say, the mental model. That's the hope. So besides the generation like this, you can also.
One more question for you.
Yes.
So I see, like right now we have a pipeline from text to traffic.
Yep.
But have you explored, say, feeding the traffic into the LLM themselves? So like conditional the traffic stuff.
Let me hit this magic button here. So on the very left side, this is an input traffic. This is a scenario that you start with, so that you, let's say, observe in data. And now I can do scene editing. I can ask for different counterfactual scenarios starting from that same scenario. And you can do this kind of editing. One thing I want to point out that I think is very interesting, I mean, okay, beyond this capability, if you look on the very right, you will see, I don't know if you guys can see my mouse, but on the very right, I have this prompt for speeding up cars that are moving in the same direction. What's very interesting is, and you might have to have very good eyes here, but there was this blue agent in the kind of behind this red and orange agent here in the second last one. And when I say speed up cars that are moving in the same direction as the ego vehicle, I think the ego vehicle here is the red one. It knew to move the blue agent to the right because otherwise it can't speed up, right? Because these other two vehicles, like, this orange one is turning. And so that's why the red one has to slow down or whatever. But it knows that if I want to speed up cars moving in the same direction, I actually have to make the room for it. So I thought it was kind of interesting to see that, as a part of that training, it learns a little bit of this, I'm not going to call it common sense reasoning, but it learns this, let's say, understanding of how traffic behaves and how traffic patterns actually look like. So I'm going to wrap up here and then, open it up for questions, but I'm going to wrap up here by kind of, we've talked about a lot of things here. And, some questions might be, okay, how can I actually try this myself, right? If I find this interesting, how can I even do this? So the good thing is, I think there's really never been a better time to do AV research. And the reason I say this is because there's like thousands of hours of public open source data from many different locations in the world. And I'm showing here some example and some, plots of their size. However, each of them are in a unique format, which makes it really frustrating if you're a researcher trying to actually work with multiple data sets, like I was some years ago and like many others were as well. So one resource that I want to share is that in the group from a few years ago, we actually made a unified data interface to multiple of these trajectory data sets. We standardized their data. We have converters for each of these to a single unified standard representation, not just trajectories, but also their maps. And, it's all open source. So I just want to say, if you are indeed interested in this space but you find it daunting, right? The amount of data sets and their things, and their different formats and all the work you have to do, just know that there is help out there. And I highly encourage you to take a look at Traj Data, which is our effort in this space and which we use internally in the group in NVIDIA. Something else I want to point you to is, if you're interested in simulation, we've also open sourced our basically our software framework for doing, all the infrastructure around simulation, or that has the models in there or different metrics that I talked about just in this little last stanza. And then, of course, I also want to talk about, I've only scratched a few directions in the group. And even then, I've only scratched kind of the past, maybe one or 2 years of research in the group. I mean, to be fair, we are a newer team within NVIDIA, but the team does, much more research covering not just novel end-to-end architectures, but the use of foundation models for AV development and AV stacks. Much more questions on simulation, not just traffic simulation, but even sensor simulation. How do you do this efficiently? How do you do this realistically? How do you combine it with traffic simulation? And then, of course, big topic that I didn't touch at all today is AI safety, right? If you have a lot of these black box learning-based models running on a car, you got to ensure that they're safe, right? You can't, it's not the Wild West here anymore. So, with that, I think the message I want to impart among all of this work is the core ideas of behavior prediction. Although, of course, they apply to the task itself, they apply really much more widely across the entire AV stack and its development. So, what you learn in this section, you can, try and see for connections to other parts of robotics. The other thing I think, I've talked a lot about this open loop, closed loop gap and all this. Closed loop simulation is really, I mean, I see this in industry, but I think, even in research, especially so, closed loop simulation is really, I think, making that capability really solid and usable by all is going to be a major enabler for speeding up the development of autonomous vehicles, and especially if you have realistic agents or realistic sensor simulations. And finally, even though there are autonomous vehicles driving around today, like in San Francisco, or I think even in Pittsburgh, there are many, many open problems that actually necessitate further research. And if you do want to research, the good thing is it's never been a better time to do that research. So yeah, I want to thank you all very much and open it up for any questions that remain.
Thank you.